carbonyl in the and the base model to power. The main will be given by Dr. Li.
Mr. Chairman, ladies and gentlemen, the title of my presentation today is Highly Dispersed Platinum Catalysis Derived from the Intrazeolite Non-Carbonyl Cluster. As we know, highly dispersed transition metals have been extensively studied because of their important roles in catalysis and in material sciences. Metal clusters are very good candidates to prepare highly dispersed metal catalysis. However, metal clusters supported on the internal surface of supports are very easily to aggregate during treatment or reaction conditions. To overcome this disadvantage, a new technique, which is called shaping photosynthesis, was developed. This technique concerns the synthesis of molecules with appreciated size in cages of zeolites. Zeolites such as X and Y type zeolites have silver cages which were connected by smaller windows. Once a molecule with appreciated size is synthesized in the silver cage, it is difficult to move out. So, by this way, we may derive some highly dispersed metal catalysis. Till now, many carbonyl clusters have been synthesized in X and Y type zeolites, such as rhodium, iridium, rhodium iron, palladium, iridium, and osmium. In our previous work, we synthesized a series of platinum carbonyl clusters. Here is platinum 9 and platinum 12 carbonyl clusters. The synthesis procedure of intrazeolite platinum carbonyl clusters is shown in this figure. Starting from sodium Y zeolite by ion exchange method, we can get platinum ammonium sodium Y sample. Then this sample was treated by two ways. The first is evacuate the sample at 353 K for 2 hours, and then introduce seal to carbonylize the sample. After we treat the sample at 373 K for 20 to 30 hours, we get a yellow-brown colored sample. Its IR spectrum is like this. It shows two very strong seal bands at 2056 and 1798 wave numbers. After we oxidize the platinum ammonia sodium Y sample at 573 K for 2 hours, and then we introduce seal to recarbonylize the sample, we get a dark green sample. Its IR spectrum is like this. It also has two very strong IR seal bands at 2080 and 1824 wave numbers, accompanied with the IR spectrum and exhaust TBD results. We concluded that these two samples were introduced for platinum 9 and platinum 12 carbonyl clusters, which were synthesized in cages of sodium Y zeolites. The next step of our study is to study the dispersion of catalysis derived from the intrazeolite platinum 12 and platinum 9 samples. The preparation of the sample is shown in this figure. First, we oxidize the intrazeolite platinum carbonyl clusters at 623 K/12, and then reduce the sample at 593 K/12. We got reduced samples. We designated the two samples as platinum 12 sodium ion and platinum 9 sodium ion. As a comparison, we also prepared platinum alumina sample. This sample was prepared by conventional impregnation method. Before use the sample was reduced at 573 K/12 in hydrogen. The first technique we use is to study the distribution of the sample of platinum particles as exhaust technique. After the sample was in situ prepared in the reactor, then we move the sample into the exhaust cell on the nitrogen atmosphere, and then we seal the sample in the cell on the hydrogen gas, and then we take the exhaust phase. As a reference to analyze the platinum bonding. As a reference to analyze the platinum bonding, we also measured the exhaust of platinum foil. Here shows the exhaust data of platinum foil. A is the Cas3 order-weighted exhaust oscillation. The B is the associated Fourier transform. In the Fourier transform, we can see that at 2.6, 3.7, 4.8, and 5.4, there are 4 peaks. These 4 peaks are due to the first neighbored platinum bond and the second, third, fourth platinum shell. By reverse Fourier transform and co-fitting method, we analyze the atomic distance and the coordination number data for platinum foil. The results are shown in this table. We can see that for platinum foil, the atomic distances and the coordination numbers for the first, second, and third platinum shells are very consistent with that of platinum methods derived by XRD technique. Here shows the exhaust data of platinum alumina. On the Fourier transform of platinum alumina, we also see that the 4 peaks appears on the figure. The analysis results of platinum alumina, from the results of the analysis of platinum alumina, we can see that the atomic distances are very similar to that of platinum foil. But the coordination number is somehow smaller. It is suggested that on platinum alumina, the platinum atoms in platinum particles having the same packing form as in platinum foil. It may take the FCC configuration. In figure C, it shows the Fourier transform of platinum 12 sodium ion. On this figure, we cannot see any peaks appeared in the high R region. The absence of peaks in high R region may suggest that the platinum particles in platinum 12 sodium ion is too small to show any contribution from far neighbored platinum shells. So it's suggested that the platinum particles in platinum-12 sodium Y is much smaller than that of platinum foil and platinum aluminum. And the analysis results also support the conclusion. We can see that for platinum-12 sodium Y and platinum-9 sodium Y, the atomic distances is similar to that of the first labeled platinum-platinum bond, but the total number is much smaller. To get more information about the distribution of platinum particles in our samples, we also measure the hydrogen and CO absorption, chemisorption on these samples. Here shows the incidence of CO and hydrogen absorption on platinum-12 sodium Y. The absorption amount was derived by extrapolating the incidence to zero pressure. The chemisorption data was listed in this table. On this table, we can see that for both platinum-12 and platinum-9 sodium Y, the strong hydrogen absorption, the hydrogen to platinum ratio is about 0.9. It is stated that the platinum atoms in platinum particles of platinum-12 sodium Y and platinum-9 sodium Y most of the atoms in these samples are accessible to hydrogen. For CO absorption on these samples, the CO to platinum ratio is about 0.69, 0.64. It is also consistent with CO absorption of highly dispersed transition metals as reported in literature. The coexistence of two kinds of carbonyl, linear CO and bridging CO, leading to the CO to platinum ratio less than even for 100% dispersion of platinum particles. For platinum aluminum, the hydrogen to platinum ratio and CO to platinum ratio are much smaller. It is in accordance with the poor dispersion of the platinum particles in platinum aluminum. In the case of rhodium and iridium, in the case of intrazeolite rhodium and iridium carbonyl clusters, after reduction, the carbonyl clusters can be reversibly regenerated by carbonylation, as shown in this table. But what our intrazeolite platinum particles, platinum carbonyl cluster will act, then we also recarbonated our reduced platinum sample. Here shows the air spectrum of the recarbonylation of platinum-12 sodium Y. When we introduced the CO in this sample, two peaks, very strong peaks, appeared at both linear CO region and bridging CO region. When we increase the temperature and prolong the time, the intensities of the bands may increase, but not change very much. From the spectrum, you can see that it is very different from the precursor spectrum. Yes, here is the precursor platinum-12 sodium. Here is the platinum, the recarbonized platinum sample. So we can conclude that after reduction, the platinum carbonyl clusters cannot be reversibly regenerated. It is different from that of rhodium and iridium. So the there is a question why the platinum interzeolite platinum carbon clusters act so differently with rhodium and iridium. I think this may be due to the differences of cluster structure between these two kinds of clusters. For platinum carbon cluster, its structure is triangular prisms. The structure after reduction, the structure is not very analytically stable. So after reduction, yes, here shows the structure of platinum carbon clusters. After reduction, the platinum atoms may change their packing forms to more analytically favorable structures such as closed packings. But for rhodium carbon clusters, its structure is octahedron. After reduction, it may easily to keep its structure. From the other discussion, we can conclude that first, highly dispersed platinum catalysts were derived from the interzeolite platinum carbon clusters. Second, after reduction, the interzeolite platinum carbon clusters cannot be reproduced by recarbonylation. This may be due to the packing form changes of the atoms in the platinum particle during reduction. This is all. Thank you for your attention. I didn't do that work, but another student in our laboratory do support platinum carbon clusters on zeolite. He found that the clusters is somehow easier to aggregate during the treatment. So I didn't show the data here. Another student do the experiment.
For instance, the host only are used on the cage, I cannot use on the surface. This something else. But I think we have prepared some clusters that can support on the aluminum. And there are also some very fine refining of the specs of the cluster. So I suspect that we prepare the cluster support on the aluminum. There's also support on the cage.
Yes, I know what you mean, but I didn't do that work to support platinum carbon clusters on aluminum. So I cannot compare the data with the interzeolite platinum carbon clusters.
From the Institute of Chemical Physics. I have a question. As we know, MSR is very effective for the distance of R, less than 3 electrons. But in your MSR result, some data show that the distance of R larger than 3 electrons, such as 4 or 6 electrons. Fortunately, as you know, MSR is effective technique for the distance of R, less than 3 electrons. But in your table, I don't know if this is table. The distance of R in your table gives us the distance of R larger than 3 electrons.
Yes,
Four or
yes.
six less.
There's four.
4 or 6 less.
Yes, and for the second platinum coated shell and the third platinum shell, surely the platinum distance is at about 4 and 5 extra. But I think that the exact data may be difficult to analyze. The atomic distance is less than 1 extra. But for larger atomic distances, it's work as well.
And cannot get a very exact result for the distance of R larger than 3 electrons. This is my opinion.
But later I saw many results which is due to the higher R regions. Really, there is. And we analyzed our samples. We got our results efficiently.
I have 2 questions. One is about the observed stoichiometry. For the hydrogen cases, it's almost stoichiometry is 100% stoichiometry. If carbon monoxide, you have only 16%. I wonder why there is the difference in the stoichiometry in the CO2.
Between the field absorption and hydrogen absorption, why is it different? I think for hydrogen absorption, one hydrogen can absorb one platinum atom. But for CO absorption, because of the existence of breathing CO, one CO can occupy 2 platinum atoms. So this is the main reason.
You have a lot of video copy observed by your FPIR. There is all platinum atoms are so-called exposed to surface. So you must have a CO of those sources should have a very near to 1. So I have a question. The second question is your cluster, number of platinum clusters is 9 and 12. It is a very small size of cluster. So it is easily migrated to the tables. The size of the table is 7 I think with the platinum 9 and platinum 12, maybe less than the size of the 6 from 7 So it means that the platinum cluster can migrate through the channel to make a big particle at the elevated temperature. Did you do that an experiment?
You mean that after reduction of the platinum particles?
After
Yes.
reduction?
Yes, after reduction of platinum particles, for 9 or 12 atoms may have a size about 7 or 8 electrons. But before reduction, our platinum carbonyl cluster is large enough to, it's almost full in the super cages about the length of the sizes of platinum carbonyl cluster is large enough to which cannot move out from the cages. So I think during the reduction and oxidation treatment, the platinum cluster cannot be moved.